and welcome to your first video on Introduction to Kinetics. We're going to talk first about something called collision theory. Collision theory is based on the idea that in order for a reaction to occur, the particles that need to react, or the particles we want to react, must somehow collide with one another. So collision theory says in order for a reaction to occur, molecules must collide with proper energy and orientation. The energy part means that they have to hit each other hard enough. We kind of talked about that a little bit. We also have to have them aligned properly as well so that they're able to form new bonds. So there are 5 major factors that affect the rate of a reaction. And you have to be able to talk about them in terms of collision theory. So if we increase temperature, particles are going to collide more frequently and with more energy. This is going to make it more likely for them to react. Therefore, increasing temperature increases reaction rate. And also, if we decrease temperature, less frequent collisions because particles are moving slowly, and less likelihood that they will react because they will have less energy when they collide. Concentration I like to think of as crowdedness. So if you increase concentration, particles are going to be more crowded, and therefore they are going to collide more frequently. Not necessarily going to have more energy when they do collide, but increasing the amount of collisions will increase the likelihood for a reaction to occur. So you're going to have an increase in reaction rate. Surface area has an effect on reaction rate as well. If you increase surface area, and keep in mind this means that you have decreased particle size. So you've broken something down into smaller pieces. This gives more places for collisions to occur. You imagine a big lump of something, the particles in the middle aren't able to collide with anything, so they therefore are not able to react. So more places for collisions to occur means a greater likelihood of reactions, and therefore an increase in reaction rate. We'll speak more about catalysts separately, but essentially what you need to know about a catalyst is that by adding a catalyst, you're going to help collisions happen in a better way. In other words, a more efficient way. There are a number of different ways catalysts work. You've talked about enzymes before, but this will increase the rate of a reaction. And also frequently make it so that a reaction can happen at a lower temperature. What you need to know about nature of reactants is that obviously some things react faster than others. In general, ionic compounds react faster, and kind of organic or more covalently bonded molecular react more slowly. And this will come into play in a few places. Just a general thing to keep in mind right now, ionic reactions tend to happen much more quickly. We've seen that a lot in lab. Please keep in mind that all reactions include an endothermic first step, where initial bonds are broken. And then there's what we call kind of this high energy intermediate. This is also something referred to as a transition state. We talked a little bit about this in our bond energy unit. You don't need to know the details of this. It's just the idea that we've broken initial bonds, but we have not formed new bonds yet. So in the initial breaking phase, energy is being put in. Then we have a bunch of stuff that's rearranging before an exothermic second step, where new bonds are being formed, and we get our products. And you'll remember from before, there's a balance between whether or not we put more energy in or get more energy out that predict if the reaction will be exo or endothermic overall. So one thing we need to be able to read is a potential energy diagram. Potential energy diagram is telling you the amount of energy you start with, how much energy you need to put in to kind of get things going, and then the amount of energy you end with. So the potential energy of our reactants is the energy stored in starting substances. The potential energy of your products is the energy stored in the bonds of your final substances. Potential energy of the activated complex just means the maximum energy after initial bonds have broken before new bonds have formed. So it's that middle state, that very high thing up in the middle. And the activation energy is energy needed to break initial bonds. So one thing we're going to talk a little bit about that we have mentioned before but not gotten into very specifically is something called the heat of reaction. And this is the net energy absorbed or released by a reaction. And this actually takes into account the fact that we have to put some energy to get things started, and we'll get some energy back out. The above diagram is representing an exothermic reaction, and we can actually tell this by looking at the fact that it ends lower. When we talk about how we're going to find what's called our delta H, I know this looks a little bit different in your note packet. The delta H is represented on here by E, and we actually find this by subtracting B minus A, and that's important. It is actually ending minus what you started with. So this exothermic reaction right here means energy was released. So we end with products that have less energy than those we started with. So an exothermic reaction is actually going to have a negative sign in front of its delta H value. Ultimately, heat is going to be released. An endothermic will have a positive delta H. Heat is absorbed. And again, sorry, that's a little redundant. This means energy is being released. It's very important to remember that we always do have those first steps. We first have an endo step where initial bonds are broken. We will then have an exo step where new bonds are formed. It's the balance of those two things, how much energy is required to break or form, that will tell you if you have an exo or endothermic reaction. And this ties into both bond energy and numbers of bonds broken or formed. So we can also have a potential energy diagram for an endothermic or energy absorbing reaction. In this case, we can start wherever. We're still going to go up in that initial step, but we end up a little bit higher than we used to. So the amount of energy right here is indicating our reactants. This little section of energy here is our products. Our activated complex is the very highest energy spot right up here. Activation energy is how much it takes to break the initial bonds and get the reaction going. And our heat of reaction, I'll do this in blue, we would actually do B minus A again and get a, delta H for E. What is different about this one is the energy of the product is higher than the energy of the reactive. And this will give you what we call a positive value, or B minus A in this case will be positive for your delta H value. And tomorrow in class we will be looking at reading potential energy diagrams.